Hi everybody, I hope that you guys had a good week last week and are doing well this evening. Yes, to answer that question in the chat, as somebody also answered, thank you for doing so. I send out a Google form about halfway through the live stream. There you enter in your PDX email, name, and your professor for the Bio 212 class, and then I take that information down, it gets to your professors, and that is how they administer extra credit. Yeah, of course. Of course. I found these helpful last term, and I really like biology, so this is a pleasure. Alrighty, so today we're going to be talking about effects of selection on population. And I'm going to go ahead and pull up the worksheet. This should be in your Canvas somewhere where your professor put it. We're going to be talking about the three different types of selection. I've drawn them out here and I'll go through them with you guys. So, one, what effects can natural selection have on populations? For example, what types of selection can occur in a population and how are these defined? So I've drawn some of these out for you and I'm going to go through them with you. So this first picture to the upper left is an example of directional selection. Selection can either be directional, stabilizing, or disruptive. This is directional selection. And this is basically if selection removes individuals that show extreme forms of a phenotypic characteristic so that the mean for the characteristic appears to move in a more positive or negative direction, aka directional selection. Another way to say this is that it basically selects for one extreme and against the other. So as we see here, the original is kind of shifting this way. It would be the same if we saw a graph with the original like this, and then new mean shifted that way. This is another type of directional selection. So I'm going to write selection for one extreme and against the other. Awesome. If we look down at number 2, this is an example, graphical representation, I think, of stabilizing selection. Stabilizing selection is something where it acts against both extremes at the same time so that the characteristic actually appears to stabilize around the mean. So that's why it's called stabilizing. So moves towards mean. Great. And finally, our last is disruptive. And disruptive selection is when the selection acts against the mean or the average phenotype. So it leads to production of polymorphic population wherein the selection is for the extremes. And that's what we see here, where the extremes were selected for, and the original population showed more of a mean average, and now that mean has depleted. Oops, weird and cool. So those are the three that we are working with today. When we move forward, we'll be discussing different scenarios and talking about, is selection occurring? Is fitness there? How should we characterize future behavior in populations given what we know now? And these kinds of selection are a good indication of what we can see future trends of. So I'm going to go ahead and scroll down. And this is the part 2 that we will be using for answering the questions for each scenario. So A, decide whether or not natural selection is operating. In doing this, indicate whether there is variability in the populations. If no, what does this imply about evolution? And if yes, what is the nature of the variation? For example, what characteristics must the variation have for selection to operate on it? B, is there any indication that members of the population differ in fitness? So this is where we're talking about fitness. Here we're discussing whether selection is operating. If no, what does this imply about the operation of natural selection? And if yes, describe the difference in fitness. And lastly, C, given the answers to A and B, what trend should characterize the future behavior or composition of the populations? And be sure to indicate any assumptions you make answering the questions. Awesome. So we're going to move forward, and basically we're going to be answering these like A, B, and C, coming back to address these 3 parts of each scenario. And one of the ways to go about this is to first ask what is being selected against, and then whether or not it's a phenotype that could be genetic. So a trait that is inherited genetically. If that answer is yes, then selection is likely, because if it's passed down from offspring and something is being selected against, where, like, what's an example? If chocolate ice cream is super selected for, it would be selected against. A lot of people would have it. There would not be a lot of chocolate ice cream left. But if the only way that chocolate ice cream could be in stores again was if surviving chocolate ice creams made chocolate ice cream offspring, then that would be a genetic basis. And so if you take away all the chocolate ice cream, there's no way to see it again in stores. That's not the best analogy, because obviously ice cream cannot reproduce. I was at a loss of analogy, so bear with me, and if there's any questions, of course, please put it in the chat. Okay. So, scenario 1. A particular species of mouse feeds on the seeds of a single species of cherry tree. When the mice eat a seed, they digest it completely. The mice choose to eat seeds of intermediate and large sizes, leaving the very small seeds of the cherry uneaten. Yeah, a chicken, for sure. So, a chicken is a better representation because they actually use offspring. So if there's a chicken with brown fur versus a chicken with white fur, and if the chicken with brown fur are preferred for meals, and it doesn't matter whether it's both female or male, but it's genetic, and you take away all of those brown chickens, and there's no way to get another brown chicken because there's only white chickens left and they cannot produce brown offspring. So I hope that helps. There are many other analogies for such scenario. Okay, awesome. So I'm going to use my highlighter and go through this and just try to analyze it a little bit. So it's saying that the mice choose seeds of intermediate and large sizes, and we know that they digest it completely. That means, that is assuming that they don't interbreed. I'm not trying to get all genetics with it. I'm not trying to get all, allele this, allele that. It's just supposed to be a simple analogy that if there's brown and white chickens, and brown or just brown can only make brown, that sort of thing. Yeah, it was just supposed to be simple. But yes, that's a good question for future genetic questions. Cool. So they digest it completely. That means seed and all. So we know that they can't make seeds of the same sizes, and they leave the small seeds uneaten. So we can say in this case that selection is in fact occurring. The variation that we're seeing is in the sides. The size of the cherry seeds is the variation that we're seeing, and so we're assuming selection is occurring, and that assumption is under the fact that the cherry seed size is heritable. So we just want to make sure to write that in A. So selection is occurring. Variation is in size of cherry seed. And this is under the assumption that seed size is a heritable trait. Awesome. And then B, and this is asking about whether members of the population differ in fitness. And in this case, we would say yes. There is a difference in fitness because the mice are selecting against the large and intermediate seeds. Cool. So this means that more small seeds will be left and will reproduce a lot of the next generation of cherry trees. So just small seeds left to reproduce. And finally for C, this is asking what kind of trend or behavior or characterize the trend, future behavior, or composition of the population. So we can say that if the selection occurs over a very long period of time, future generations of cherry trees would produce smaller sized seeds. And cool, yeah. I did see that comment earlier about answering that type of selection. I just wanted to address it when I was like finished answering the question and stuff, but that is correct. And this would be a directional shift where we are selecting for one extreme, in this case small. And so the bigger seeds would get digested and taken out of the gene pool, as well as some of the median. And so the smaller seeds will go on to reproduce. That is exactly correct. The next question is asking to graph the abundance of the different sizes of cherry seeds over 10 seasons. So I pre-drew this just because of to save time and take time to explain it. And so we're seeing, time increasing this way. And this trend is similar to what we said above, wherein the small seeds would increase in abundance. You can see on the left side of this graph that this arrow shows an increase in cherry seed abundance, and that the medium and large seeds would show a trend downward over generations. So they're decreasing while small seeds are increasing. Awesome. To take this even further, because there's going to be more small seeds and fewer intermediate and large seeds, those could become scarce enough that the lack of food availability may also put selective pressure on the mice, and that could be a different type of selection to be tested later. Cool. I can put it in right now for you, no problem. There you go. Awesome. Yeah, no problem. Cool. Scenario 2A. A small island A contains 3 separate populations of a single species of cherry tree. The seed size varies between trees. That is, some trees produce seeds that are all in the small size ranges. Others produce seeds all in middle size, and others produce all in large size ranges. A small population of mice is introduced to the island. The mice eat cherry trees and are the only predators on the cherry trees. When the mice eat a cherry, they completely digest it and the pit or seed inside it. The mice choose medium and large seeds and leave the smallest seeds uneaten. So this is somewhat similar to the last scenario. The only difference is now we're seeing that instead of just cherry seeds on their own, now we know that one tree only produces one size of seeds. One tree only produces small, medium, or large, not any of them in combination. And so in this case, for the answer to A, we would say selection is occurring where the variation again is in cherry seed size, and once again we would have to assume this is a heritable trait for selection to be occurring. Relating it back to fitness, this would mean that the individual seeds do differ, because the mice are selecting against the very large and medium seeds. Cool. And so that means that more small seeds, oh my gosh, small seeds, say small seeds 5 times fast. Many more small seeds will be left relative to other sizes and would produce the next generation of cherry trees. And lastly, about future trends, the future generations of cherry trees will produce more small seeds. And if the three populations, each made up of trees with different, the population with small seeds of the trees will become much larger over time compared to the other two populations, is what I'm trying to say. So future generations the cherry seeds will trend towards small. Awesome. Similarly to the last question, this one asks us to graph and a similar trend where the small cherry seed size would increase over time because the medium and large seed size are being selected against by the mice because they're eating them all for food. So over time, there will be fewer cherry trees that produce those large and intermediate seeds, and there will be many more that produce small seeds and could, once again, cause selective pressure on the mice, perhaps. Okay. Scenario 3B. Would your answer for scenario 2B, sorry. Would your answer for scenario 2A change the following, given the following information? As you continue to study the population of trees, you note that the viability of the seeds varies with each size such that the viability of the small seeds is less than that of the middle-sized seeds, which is less than that of the largest seeds. And once again, we're going to answer A, B, and C. Oh, no problem. We could say here, once again, that selection is in fact occurring. And that the variation is still in size because the size is now determining the viability. And once again, we're assuming heritability. And for B, in this case, the individual seeds do differ in fitness. And in this case, the more small seeds, it's a little tricky just because the viability, we do have to take that into account. And so if the mice are still selecting against the large and middle seeds, then only the small seeds are not eaten. And so, because a lot are left relative to other sizes, they will be more likely to reproduce, but also because the difference related to seed, in the fitness related to seed size, the larger the seed, the more likely it is to survive and reproduce a new tree. So it's a complicated fitness trade-off where small seeds left behind can produce future generations with low viability, which means, like, if they produce a lot, they might not even survive. That's kind of the caveat. And large seeds get selected against but are more likely to survive and reproduce. And finally, because of this complex scenario, we need to consider the effects of both the selection by mice and also the fitness of the seeds with the tree. And so if the mice are not eating all of the large and middle seeds, some will remain and produce much of the next generation. And so the future populations, the proportion of the trees producing each seed type depends on both the numbers of large, middle, and small size seeds that are uneaten and the relative viability of these. So, to say that in short, depend on number of large, medium, and small size seeds, as well as each's individual fitness. So, in a very long sentence, it depends. If a mice forgets to eat a large seed, that is a lucky thing for the mice, even though he doesn't know it, and the seed, because that enhanced viability, or because of their greater fitness, because they're more viable, they're more likely to reproduce, produce a lot more cherry trees, produce a lot more offspring, even though the small size seeds could have a lot of them. If there's low viability, many of them might not even survive to reproduce. So, yeah. Alrighty. Moving on to 3A. Small island B contains 3 separate populations of a single species of cherry tree. Unlike the species on island A, in this species seed size varies within trees. That is, each tree produces seeds that range in size from large to small. A small population of mice is introduced to the island. These are the only predators on the cherry trees. When the mice eat a cherry, they digest it and the pit or seed completely. We heard this before. The mice choose medium and large seeds and leave the smallest seeds uneaten. Okay, now this one is even trickier, I know, yay. But now we have to take into account even a little bit more than what we did before. So to answer A, we could say that selection is occurring if we're assuming that seed size is heritable. But that's if each flower on a tree is independently pollinated to produce its seeds. Then the individual seeds on a tree can have different combinations of genes. But more likely, if you were to notice that more shaded parts of the tree produce smaller sized cherry seeds and the sunnier parts produce cherries with larger seeds, and then in that case we would have to say that it may be the result of available nutrients and not necessarily genetic differences. And so because we're going to be taking this into 2 kind of parts, we're going to look at this scenario in terms of no selection because we're noticing that it's a result of available nutrients. And I know that's not explicitly said here, it's just for the tutoring purposes, it's just to give you guys different kinds of scenarios. Of course, if there were questions relating to the types of selection, the scenarios that you would be encountering would be very explicit. Cool, and for B, then if seed size varies with nutrition, selection against large and small seeds is not necessarily selection against a genotype, because no matter what the genotype is, so in this case, more based on, yes, exactly, that's exactly right. So in this case, we can't say it's genetic because if the seed size has shown to be bigger when it's in more sunlight and more available to nutrients, but in the shadier parts of the trees, we see smaller seeds. Yeah, awesome. So, selection is not against any genotype. And so there's no relative difference seen in fitness. And finally, C, if there are no selection and no differences, then the population should remain stable in future generations. Alrighty. The next part of this question asks us to graph, and looks pretty similar to the graphs that we saw previously, but because the population remains relatively stable, we're just going to see like ebbs and flows of all of them is what this is supposed to show. There's not one that will show growth over generations and one that will actually be selected for. There's no selection occurring, and so it's a pretty uniform graph. Alrighty, scenario 3B. Would your answer for scenario 3A change given the following information? As you can continue to study these populations, you note that the viability of the seeds does not vary with size. Over time, however, you find that the trees that grow from the smallest seeds produce fewer large seeds. So to answer your question, you're super close, not quite. So the reason why there's no selection is because in our little teacher notes that they like to throw in for me, we were assuming that we saw the variable of sizes based on sunlight availability. So we noticed that in shadier parts of the tree we had smaller seeds, and areas where there was more access to sun we saw larger seeds. So from there we deduced that it was not genetically linked, that it was nutrient linked. So the ones that had more access to that sunlight and that nutrients actually grew bigger than the smaller ones that didn't have access to sun. That's why we determined that there was no genetic heritability, and when there's no genetic heritability, then there's not selection. Does that answer your question? Yeah, of course. I also probably didn't explain it. So thank you for answering those questions, because I'm sure if you didn't hear it, other people didn't as well. So yeah, thanks. I do appreciate it. Sorry about that. Okay, sorry. So the viability of the seeds does not vary with size, and you find that the trees that grow from the smallest seeds produce fewer large seeds. So this information would provide additional evidence that is needed to prove that seed size is heritable and not the result of growth conditions, because it's saying that small seeds to grow and produce trees actually produce more small seeds than medium or large. That's an indication of genetic heritability, and so we can say that selection would be occurring. Variability in seed size, and assuming heritability. Cool. In this case, we're seeing that small seeds would survive more frequently compared to medium and large. So that would eventually be removed from the population. So therefore, all we would say for this fitness aspect is that small seeds would survive more frequently, because the mice want to eat the bigger ones. And then over time, we would expect to see more offspring from small-sized seeds and as a result, more production of small-sized seeds. It says May. No. All right. Yes, that is exactly right. So that's why eventually we would see a large increase in medium and large sized seeds, was because when the mice are eating the large and medium and they're selecting for small, and the small are growing and they only produce a finite amount of those large and medium seeds, they produce many small. We could say that's genetic. So yeah, exactly right. What you said is exactly right. Okay. Scenario 4. After a severe spring ice storm, about half of the finches in a population are found dead. Examination of the dead bird indicates that they vary in age from young to old. About 60% of the dead are fledglings or just left the nest, and 20% are over 3 years of age or old for the species. Oh, sorry, I didn't mean to come off as blunt or rude. I just realized I was repeating what you said. So I was like, yeah, exactly what you said is correct. Sorry. Okay. All right. So for A, to decide whether or not this is selection, because it gives us the information that 60% of the dead. Um, oh, yeah. Sad. Oh, sad. So, because 60% of those found that have passed are very, very, very young or old for the species, I would argue that this is actually not selection. Because the majority of the birds that were found deceased are actually those that aren't able to survive, based on their general health and level of experience. So, for example, like younger birds that are not able to survive without help are going to be more vulnerable in an ice storm situation, as well as older birds who may not have the strength um, to survive through things like that have passed. So the characteristics that are selecting for the very, very young or the very, very old are not necessarily biased. They just happen within nature. And so there's not going to be a lot of genetic differences in the individuals compared to the rest of the population that survived. So no genetic bias, and that's important to jot down. Yeah, kind of. So it's not like that their health is bad. It's just, they're just in a vulnerable state. So everything, when we're babies, we're most vulnerable to infections and things like that. So it's kind of It's like what you're saying, except I don't want to also say that they have like decreased health in terms of disease or anything like that. It's just that they are generally weaker. It's not like if younger birds live. Right. Exactly. And the ones that are dead are from the same. Yeah. Exactly. No. Oh, yeah. I mean, yes. Right. Um, it's not a selection based on their age or anything like that. It's not a genetic bias thing because, yeah, those young offspring were probably going to grow up. It's not like they have a selection where young offspring are actually, passing. Um, so to answer for B for fitness, yeah, like the elderly, exactly. Elderly and young are having a harder time. They're pushing, boosters for more of the geriatric population and those 50 plus. So that's why they're kind of pushing that, is because of the weaker immune system. Um, and that's why a lot of times when things like vaccination comes out, they really push it for the geriatric population. Right, exactly. Yes, guys, you guys all got it down, dude. So if this were selection, it would be against young and old ages. And if we took this into extreme, we would have to argue that over time, each subsequent generation would have more middle-aged individuals if it were selecting, like we're saying in the chat, compared to members of old and young. And because it's selecting for middle-aged individuals, it doesn't make sense because they would have had to be young at some point. You can't just like skip over and be middle-aged and then be selected for. So that's why we can argue there's no fitness difference other than sometimes my mouth is faster than my hand. Other than the fact that the young and the old were vulnerable in this situation. Cool. And so C, without any more information on this scenario, we can't say that genetic selection occurred, so we wouldn't see a better way to say this is we would expect to see no significant changes in the genetics of this population over time. Fitness does not. Let me think about that, because I also don't want to just give you an answer that is not correct. It does and it doesn't. So fitness really depends on the ability of an organism to survive and reproduce in a given environment. So it really has to depend on where they're living, because if they have certain phenotypes that increase the fitness of an organism, that's why we use analogies like on a white sand beach, there's white and black mice, and a hawk preys on its ability to see. We would say in that case that the white mice has an increased fitness because in that environment it's more likely to survive and reproduce. Whereas a black mice would have a lower fitness in that case. So that's kind of what fitness does. It's not like individual allele is better or this or that or this. You can look at it microscopically. When you go through genetics, you'll talk a lot about traits, heritability, and fitness and things like that. So you can think about it on an individual allele basis for sure, but it's more how that allele is expressed, which allele is it in its environment. So it can get a little bit more complicated, which is why I kind of hesitated. But I hope that clarifies. And let me know if it does not, because I can totally try again. Right. Yeah, sorry, I go down rabbit holes. I did not mean, but cool. And yeah, it wouldn't be considered natural selection, because if it was selecting against the old and the young, then we would see more of it. If it was selecting against the young and the old, we saw an increase of middle-aged people, it wouldn't make sense, because they would have to be young at some point, and so that's why that doesn't work. And that's why it's not considered natural selection, because it's not one favored or the other. It's just a natural event that, unfortunately killed these little birds. Yes, of course. So no significant changes in gene. Cool. Now, on to the last final home stretch. And of course, there's just a few more questions. I usually just stop at 7, but I think we can do this too. There's only 3. So, number 3. The figure below shows... Well, yeah, once you get to an elderly age, the reproductive rate does go down. But that also doesn't... That's a good question. If we saw the young in the middle get killed, there could be a few that are able to reproduce in the older offspring, and so I guess you could see some form of reproduction, but it would significantly decrease and potentially eradicate that organism. Well, not necessarily, because it's not like you can just because younger, like for example, if we saw right now, like younger and middle-aged people just, randomly die off, and the older population is left, it's not like that older population is going to have like different genes at that time to be able to reproduce. Those who can, those who can't. So I guess like over time, well, yes. Sorry, I'm thinking about this out loud. I'm a verbal processor. So if they were to continue, yeah, of course, have a great day. If they were continuing to reproduce and it was those older people who were able to, then I guess you could, if it was genetically linked, you could say that those offspring would potentially have the genes to be able to reproduce later in life as well. But that doesn't necessarily mean that they would produce when they're older, if that makes sense. I know that took some ring around the rosying, but... Okay. Sorry. Alright. So the figure below shows the distribution of a phenotypic characteristic in a population of organisms. Also shown are 3 portions, A, B, and C, of that distribution. Parts A, B, and C. For the following situations, which portions of the population will be selected against and the least likely to have their genes expressed in the next generation? So A, male sticklebacks with bright red coloring are favored by females as mates, but the bright red color also makes the males more likely to be seen by predators. So we just have to use the following set of answers to answer A, and in this situation, we would actually choose D. And this is because the brightest males are favored and also most preyed upon. So the females are going to select against the less brightly colored males by not mating with them, and they're not able to produce, but also predators are going to select against the brightly colored males because they can see them better. Okay, awesome. Sorry about that. Dull color, no mates. And this would be a form of stabilizing selection. Bright color, eaten. Alrighty. On Island Z in the Galapagos, the plant population contains only 2 species. One of the 2 plant species produces very large seeds, and the other produces small seeds. A species of seed-eating finch has lived on the island for many years. Members of this established species have large beaks and prefer large seeds. A small population of different species of seed-eating finch has migrated to the island. The beak size in the new species population varies over a continuum from relatively small to large. How will evolution of the new finch species be affected? So going through these answer choices, and we see, so the species living already on the island is large beak size. The species coming to the island is small to large. So in this case, we would see that they are selected against portion C only, because their medium and small size beaks would remain fine. It's not like they're competing for food. But the large side beaks already exist on the population, so their food is already in competition. So we would say C. And yeah, this is a form of disruptive selection on the new finch population. Alrighty, and our last one. In a species of plant-eating land snail, the shell color is variable and ranges from very light to intermediate to very dark in color. The snails are preyed upon by birds that use sight to find their prey. A small population of these snails is moved to an island where the food plants in their preferred habitat are very light in color or very dark. So, just to kind of recreate what we have on the other page. Because it's either very light or very dark, it's actually going to select against this middle B. And we're going to see increases of A and C like we do in disruptive selection. So because the snails are either very light or very dark, one extreme or the other, we're going to see less of that median. So we're going to say that intermediate snails will not have any camouflage and be selected against. Alrighty. So that brings us to the end of today's live stream. I hope that you guys had a good time, good learning experience. I threw the Google form in the chat just one more time in case you guys needed it. But if you have any more questions, I'll be here for another minute or two. If not, have a lovely rest of your evening. And I will see you guys next week. For the finches. Well, it would be, sorry. I did not speak right about that being disruptive selection. It actually would be directional selection. So because we have a range of like beak sizes like this small to large, and we move to this island, we're going to see an increase of small, medium, and a decrease of large, and that's why it's directional selection. Oh, sorry. Okay, cool. Yes, it's directional selection for their beak size. Exactly. Alright, awesome guys. It was really great getting to work with all of you. Thank you all for coming. I always appreciate it. Yeah, have a great night, everybody, and I will see you next week.